Rotation speed, VR, is the speed at which the pilot initiates action to raise the nose gear off the ground, with the intention of becoming airborne. The pilot action is to pull back on the control column. This action deflects the horizontal stabilizer to create a downward aerodynamic force on the tail. This force pushes the tailplane down and rotates the aeroplane about the main wheels, which will raise the nose wheel off the ground. The certification specifications state that VR must not be less than V1 and must not be less than 105% of VMC. It must allow the aeroplane to obtain V2 before reaching the screen height, and it must also allow the aeroplane, if it were rotated at its maximum practical rate, to obtain a VLOF with the correct speed margin from VMU. Lastly, as with other speeds, we need to examine the factors that affect VR. However, this is made easy for you. Similarly with V1, all the factors that affect VR can be found by examining page 18 and 19 of section 4 in cap 698. On page 18 and 19, examine the second table from the top. This table lists the 3 V speeds, including VR against the aeroplane mass. This table can show us what the effect of certain factors are. For example, let's look at what aeroplane mass does to VR. If the aeroplane mass was 50,000 kilograms, VR would be 131 knots under density column A. But if the mass was increased to 65,000 kilograms, then VR would increase to 155 knots. Therefore, increasing mass increases VR. The next factor to affect VR is the aeroplane configuration. Page 18 lists the V speeds for 5 degrees flaps, and page 19 lists the V speeds with 15 degrees flap. Therefore, comparing these speeds from the 2 pages should tell us the effect of the flaps. On page 18, which is 5 degrees flap, a 55,000 kilogram mass requires a VR speed of 139 knots. But on page 19, which is 15 degree flap, and for the same mass of 55,000 kilograms, the VR speed is now only 131 knots. Therefore, we can see that increasing the flap angle decreases VR. The next factor to affect VR is density. On page 17 of section 4 is the density graph. You may recall that band A is high density, whereas band F equates to low density. We can now use these bands to see the effect of density on VR. Returning to page 18, taking a mass of 50,000 kilograms in band A, which is high density, VR is 131 knots. But in band B, C, D, and E, the value of VR is increasing. Therefore, we can state that as density decreases, VR increases. In modern airliners, VR is calculated not by looking at the speed tables, but it will be computed by the aeroplane once the relevant data is inserted into the Flight Managed Computer or Multipurpose Computer Display Unit. Once VR and V1 have been calculated by the pilots, they can be entered into the flight management system and, thereafter, shown to the pilots in the speed scale on the left-hand side of the primary flight display, PFD, or the Electronic Attitude Director Indicator, the EADI, as shown on screen. Since an action by the flying pilot is required at VR, VR is called out by the non-flying pilot, and at this moment the flying pilot will initiate rotation. The speed V2 is called the takeoff safety speed. On page 3 of section 4, in cap 698, it states that V2 is the target speed to be obtained with one engine inoperative. In other words, V2 must be reached at or prior to the screen height. Why is V2 called the takeoff safety speed? What is safe about actually reaching it? There are 2 main speeds which, when flying close to, may be unsafe. The first of these is the stall speed, and the second is the minimum control speed. Therefore, in order for V2 to be called a safe speed, it must be faster than these speeds. There is another reason why V2 is called the takeoff safety speed. In the event of engine failure, V2 must be flown until the aeroplane reaches 400 feet. Therefore, the other safe feature about V2 is that the aeroplane is able to achieve a positive climb. In fact, V2 is the slowest speed which will enable the aeroplane to have sufficient excess thrust to climb above the minimum acceptable climb gradient. Let us detail the three requirements about V2. V2 may not be less than V2 min. It may not be less than VR plus the speed increment attained before reaching the screen height. And lastly, V2 may not be less than a speed that provides the minimum maneuvering capability. However, V2 min itself has its own requirements. V2 min may not be less than 1.10 times VMC and 1.13 VSR for two-engined and three-engined turbopropeller aeroplanes and jet aeroplanes without stall speed reduction regimes. Or this may reduce to 1.08 VSR for turbopropeller-powered aeroplanes with more than three engines and jet aeroplanes with stall speed reduction regimes. Hopefully, you can now see why V2 is called the takeoff safety speed. V2 is faster than both the stall speed and the control speed by defined margins, and it will also allow the aeroplane to climb at the minimum gradients. Let's assume a two-engine jet with stall reduction regimes for the purposes of an illustration. This means that V2 min, and therefore V2, cannot be less than 1.1 VMC and 1.13 VSR. Using a graph with density on the y-axis and velocity on the x-axis means that 1.1 VMC speed is plotted as shown, and the 1.13 VSR is plotted as shown. Remember, V2 min and therefore V2 are not allowed to be less than either of these speeds. Therefore, the region to the left of the plotted lines has been marked off. The speed V2 is only allowed to be in the right-hand clear area of the graph. Therefore, the minimum V2 would be the slowest speed range of the clear area. This line being drawn now shows the V2 min line. This graph is useful because changing the variable factors such as weight and flap setting, it is possible to manipulate the lines and see the effect these factors have on the V2 speed. Let us consider the effect of weight on the graph and on V2 min. Increasing the mass of the aeroplane and or reducing flap angle will only increase the stall speed. Therefore, 1.13 VSR would increase as shown. Since V2 min is not allowed to be less than 1.13 VSR, then V2 min must increase to be at 1.13 VSR. From this we can see that with increasing mass, or with reducing flap angles, V2 min increases, which in turn increases V2. If weight were to decrease, or flap angle were to increase, then the 1.13 VSR would decrease as shown. This means that V2 min may also decrease, but only until the 1.1 VMC speed. Even though the stall speed may reduce to very low speeds, V2 min cannot be less than 1.1 VMC. Therefore, reducing weight or increasing flap angles will decrease V2, but only until 1.1 VMC. To analyze more simply all the factors that can affect V2, turn to page 18 and 19 of section 4 in Cap 698. You will recall from a similar discussion on V1 and VR that these pages can show the effect of mass, configuration and density on V2. So ensure that you use these pages to see for yourself how these factors change V2. Once V2 is calculated by the pilots, it can be entered into the flight management computer, just like V1 and VR were. Having done this, V2 will be displayed to the pilots in the speed scale on the left-hand side of the primary flight display, or the electronic attitude direction indicator, as shown on screen. This completes the discussion on the takeoff V-speeds, and the image shown on screen shows you the approximate positions of where these speeds are in relation in the takeoff. The image you see on screen is actually representing the approximate positions of the V-speeds if takeoff is continued in the event of engine failure. However, there is one last speed to add. This speed is V3. V3 is the speed the aeroplane will have naturally accelerated to by the time it reaches the screen height, if all the engines are operating. It is therefore faster than V2. Therefore, V2 will hopefully have been reached way before the screen height as shown. However, if the engine were to fail, then the acceleration to the screen height would be much less, and V2 will be obtained much closer to the screen height.